Hey everyone, thank you for the introduction. So my name is Vinay. I'm a software engineer at Clockwork, and today we're going to talk. Today we're going to talk a little bit about Clockwork's product suite and what it can do to observe and control AI/ML workloads. So as a quick overview, first we'll go through Clockwork's tools for edge-based observation and control, and then we'll go over how we can actually observe what happens under the hood for some of these AI/ML workloads, specifically focusing on NVIDIA's collective communications library. And finally, we'll discuss how we can sort of speed up some of these workloads through Clockwork's two-step solution to optimize training. So to begin with, let's discuss Clockwork's product suite a little bit. The first thing we have here is a cluster of VMs. You can think about every single one of these circles as a machine, for example, renting virtual machines on, say, Google Cloud. And so the first thing we do is we install the Clockwork agent on each of these machines. And these agents are going to talk to each other by establishing what we like to call a probe mesh. So every single agent is going to talk to 5 other agents by exchanging small UDP packets that we call probes. And these probes are able to do a number of interesting things for us. The first thing that the probes will do is synchronize all of the VM clocks accurately to a common reference. So the R there denotes that one of these is the reference clock. And since we have highly synchronized clocks, we have the ability to collect accurate one-way delay measurements across the network. Since every single machine is now on the same timeline, I can take a send timestamp on one machine and a receive timestamp on another machine and accurately measure how long a packet actually took to traverse the network. And the final thing we can do is detect VM colocation. So VM colocation in this case is identifying whether 2 or more virtual machines are actually located on the same physical host in the cloud. And we're able to do this through the probe mesh by examining the frequency corrections that we measured through our clock synchronization. The final aspect of Clockwork's product suite is control. We have a technology called Packet Rocket, which is able to do accurate sensing and control at the edge of the network on TCP traffic. The sensing aspect is able to provide us with a number of interesting measurements, such as TCP timeouts, retransmissions, packet drops, and delays at the level of TCP flows. And the control aspect is able to provide the abstraction of a zero-drop network to the user. So the important thing to establish is that all of this is achievable purely in software. There are no hardware support or upgrades needed to either do monitoring or control through our software solution. And if you want to learn more, we have the 2 NSTI papers here, the first for ClockSync and the second for Packet Rocket. So I'll show you a couple of examples of what our product suite actually looks like. So the first thing that we do is clock synchronization. And this is an example run in a cluster of 100 nodes over a period of 40 hours. We see that the clock offsets relative to the reference are very tight. They're hundreds of nanoseconds here consistently over a long period of time, whereas current open source clock synchronization technologies such as NTP or Crony provide 1,000x worse clock synchronization accuracy. The second thing we can do is precise one-way delay measurements at the edge of the network. So there's 2 phases here to this plot. The left phase is without any network traffic, and Clockwork can accurately sense the base latencies in the network. These are going to be, say, on the order of hundreds of microseconds. And when we apply network traffic, Clockwork's probes can sense the effect of that traffic in the network. So our UDP probes incur delay as a result of this traffic, and so the delay is here on the order of, say, single-digit milliseconds as a result of applying the network traffic. The third thing that we do is VM colocation detection. And this is an example of a colocation result that you might get if you were to provision 50 nodes in the public cloud. A number of the hosts, as you can see, are singletons, meaning that they're not located with any of the other ones. But for many of the nodes, they are actually collocated. So every circle here is a single node, and the larger circles indicate physical hosts. So oftentimes, these VMs will be packed onto physical hosts according to some policy that the cloud provider will decide. In this case, the highest degree of collocation that we see is 4, meaning that there are 4 VMs in a physical host. But depending on the instance type and which cloud provider you're using, you can see much higher degrees of collocation as well. And the final part of our software solution is Packet Rocket, which is providing the abstraction of a zero-drop network. This is something that can be turned on and off at will. And this is an example of what Packet Rocket can achieve. This graph is measuring the total amount of dropped packets in the network over time. And before I turned on Packet Rocket in this run, we were seeing 20,000 plus drops per second. With Packet Rocket, we're able to essentially reduce this to zero, both improving the network delays and providing a better overall network for the user. So now let's talk about how Clockwork can be used to actually do distributed training. The current practice for cloud tenants is pretty simple, just rent and run. So first you rent your VMs, they'll have some GPUs attached to them. And the second is you install any dependencies that you have and you run your workload on those VMs and GPUs. With Clockwork software, we can actually optimize for the runtime by doing the following. First, you rent the VMs. Then you install the Clockwork agents on your VMs. This enables you to monitor the VM cluster, getting all of the different kinds of measurements that we just talked about before. Next, what you can do is determine VM colocation and select VMs specifically to avoid colocation. As we see in a second, this has significant performance implications and can actually improve the training throughput. Finally, we can turn on Packet Rocket, and this provides the congestion control needed to further optimize the workload, giving even more performance improvement. And finally, as you would before, you'll go ahead and run your workload. So we've talked a little bit about colocation, but how does Packet Rocket actually work? Well, transport protocols today, the top part of this graph describes what transport protocols today are going to do. So if I have a sender and a receiver, and I have a switch in the middle of the network, the sender is going to send to the receiver, and the switch eventually will incur a buffer overflow, which is going to create timeouts and retransmissions. What Packet Rocket is able to do is prevent this from ever happening in the first place. The sender is going to send traffic, and because the sender and receiver clocks are accurately synchronized, the one-way delay measurement of the TCP packets is able to be measured at the receiver. And so because the receiver knows the one-way delay, the receiver can actually send a signal back to the sender to pause when the one-way delay exceeds a certain threshold. And this prevents the switch buffer from overflowing, thereby preventing retransmissions, timeouts, and other harmful events that will adversely affect throughput. This also has the effect that it reduces the overall in-network delays because congestion is being avoided. And the important thing to note is through all of this, we still fully utilize the link. So when we turn on Packet Rocket, if you're sending, for example, iPerf traffic at 10 gigabits per second, even with Packet Rocket turned on, you'll still hit that same throughput and that same maximum link utilization, just without avoiding all of the bad things that would happen if you were just run this on the cloud without Packet Rocket. So now let's talk about observation a little bit. What can we do using Clockwork's accurate timestamps and VM colocation in order to sort of get a sense of what's actually going on when we run some training or some nickel job. So let's talk about a couple of NVIDIA's nickel primitives. There are a number of actions that you can do on a distributed cluster of hosts and GPUs. These things have names like all reduce, all gather, reduce, scatter, and these are the fundamental building blocks of any distributed training workload. So there's an example image here that describes a cluster of 4 GPUs. You can think of each one as connected to a different physical host, and each one as owning some component of a large model, right? So during the process of training, a number of data packets are exchanged between the hosts, and these things will contain parameters relevant to training, such as the model gradients or optimizer states. And so, what will happen is that in the process of training, the information is exchanged between the GPUs using the primitives listed above, such as all reduce, all gather. So for example, if one of the GPUs needs to know the optimizer states or the gradients owned by one of the other GPUs, those will all be sent. And some addition and multiplication operations will be done on the actual GPUs. So let's talk a little bit about how the ring-style communication is actually done in this case. You might think about all reduce as a simple operation where everybody is just sending to one guy, and so you have, say, 3 senders and 1 receiver, and each sender simultaneously sends to the receiver. But it turns out this isn't the actual most efficient way to implement it in a variety of cases. The better way to do it is a ring style. So what will happen is that the data packet that we're tracking will iterate through each of the hops in the ring and accumulate a sum as it goes through. So for example, this packet just accumulated the 8, the 3, the 5, and the 1 to create a total of 17. And once we have this final sum, this sum is then further propagated once more around the ring to create the final result and allow every single one of the hosts to get the result. So this ring is sort of the fundamental basis of pretty much all of Nickel's communication primitives. So we can actually use Clockwork's accurate time to take a look at the ring a little bit closely and see when bottlenecks appear. What we've done is we've taken a version of Nickel that has been instrumented to log the send and receive timestamps of messages on each of the links in the ring. And because we have accurate time, we can match the send and receive timestamps to create one-way delays and actually measure the one-way delays on each of those links. And that's exactly what this graph is showing. And you'll notice that most of them are pretty low, say on the order of hundreds of microseconds, except one of them, the link between agent 2 and agent 10, is very high. It's experiencing delays that are on the order of 12 to 14 milliseconds. And so this is the bottleneck link that is actually slowing the entire job completion on this cluster of 16 machines. And so we might ask, why is this happening? What is so special about this link that is causing the problem? And it turns out that Clockwork's VM collocator can tell you exactly what the problem is. We have this diagram on the right, which is showing the collocation pattern for the cluster of VMs that I've created. And we see that 2 and 10 are actually collocated. And so they experience contention for resources in the hypervisor. They're not able to actually pump out traffic at the rate that is promised by the cloud provider, therefore incurring a significant queuing delay on the sender, which is what's creating these very high delays in the network. And this is why eliminating collocation can actually speed up the throughput of a lot of these jobs, because we can take away the hypervisor contention here. In the absence of collocation, this is exactly what we expect to see. There are no significant bottlenecks, and they're all able to serve at a latency that is tolerable, which is, say, hundreds of microseconds to a few milliseconds. So now what can we do to actually speed up workloads distributed across hosts? Well, we can do the 2 things that we just talked about: eliminate collocation and then turn on Packet Rocket. And once we do this, we can actually benchmark on Google Cloud exactly the kind of benefit that it gives us on some of these Nickel communication primitives. So our experimental setup here consists of 16 N1 standard 16 hosts on Google, each of which is connected to 2 V100 GPUs. The GPUs on a single host can talk to each other through NVLink, while the traffic between the hosts is all over TCP/IP. And this is exactly where we play a role. So because the traffic is over TCP/IP, Packet Rocket can effectively monitor and control this traffic. So these are the results that we see. On a cloud-assigned cluster, which is the thing to the rightmost side of the slide, there's incredibly variable and high runtimes for the all-reduced communication primitive. You can see that across 3 runs, it can range from anywhere between 300 seconds to 425 seconds on this setup to do 100 iterations of this task that is a primitive in training. And simply choosing the VMs to avoid collocation already provides a substantial benefit, both in the task completion time and also in the variance of the runtimes. We said if we specifically choose the cluster to avoid collocation, we can drop down to about 250 seconds for this task. And this is pretty consistent across all of the runs. We don't see the same significant variability that we did just choosing the cloud-assigned cluster. And then the last step, which is to then turn on Packet Rocket on the Clockwork chosen cluster, provides a further improvement in runtime. And we hit about 150 seconds, which represents a 61% drop in the median task completion time. So this is roughly a 2.6x increase in TCP throughput, which is indicative of a significant performance bump. So this is actually a general property. This slide simply shows that regardless of which of the primitives you're using, all of which are important in training, we can hit a pretty substantial benefit. There's roughly a 30 to 40% benefit simply by turning on Packet Rocket sort of across the board here. So now we can actually delve into the monitoring component of our software stack and see the impact that Packet Rocket has on many of these metrics that we're surfacing. So at the top, we see the system-wide delays. This is essentially an average and 3 standard deviations above the average of all of the delays in the network with and without Packet Rocket. On the left side is with Packet Rocket off, and on the right side is with it on. And so we drop substantially from millisecond level delays to microsecond level delays, which has a significant implication on the performance. If you notice at the bottom, the actual throughput while I'm running this workload goes from about 230 gigabits per second to about 400 gigabits per second. This has the effect that we're not only able to complete the job faster, but we're able to achieve better use of the GPUs themselves. During training, their utilization will increase, and they'll actually be able to do more floating point operations because they're not waiting on the network. Finally, we can actually look at the nickel delays that we looked at earlier and see what the impact is of turning on Packet Rocket. These are the application level one-way delays in the 99th percentile, so the tail latencies. And Packet Rocket is able to substantially bring down the tail latencies across the board on all of the links in the ring, improving performance and also increasing the throughput as a result. Finally, let's talk a little bit about a popular distributed training framework known as Ray. So I'm sure many of you have used Ray, and Ray has essentially a wrapper around Nickel, which is called the Ray Collective Communications Library. This library is able to do many of the same primitives that Nickel does, such as all reduce and all gather. And so we've taken it and we've evaluated it on the exact same setup that we evaluated Nickel on. We have these 16 N1 standard 16 hosts, each of which is connected to 2 GPUs, except this time we simply slap a Ray worker on each of these hosts. And one of them will be the head node that is responsible for doing the orchestration. And we see the exact same benefit in Ray as well. We created a number of clusters of each type and ran the all reduce task for a number of iterations, and the results are the distribution that you see on the right-hand side of this picture. Once again, the cloud-assigned cluster without any of our optimizations is the worst. And simply by choosing VMs well, we already get about an 8% performance benefit here in the task completion time. And by choosing the VMs well and then turning on congestion control, we get a 26% decrease in the task completion time, which represents a substantial improvement on the Ray workloads. So just to recap everything that we've talked about, the first thing is that performance optimizations on ML workloads is a pretty hot area. There are a number of things people are doing. Obviously, there's a lot of work on hardware acceleration, either through GPUs or other custom accelerators that various cloud providers are coming up with. There's the development of communication libraries such as Nickel, which aim to optimize the communication aspect of training. And finally, there's the development of compute frameworks such as Ray. Where Clockwork plays a role is, first, we can provide very good insights into network bottlenecks and increase observability. And the second is control. We can show that by turning on our two-step optimization solution, we can significantly accelerate the communications benchmarks and improve the time that it takes to do a lot of these training jobs. Finally, when training these large models on GPUs across hosts, communication can become a bottleneck, specifically when we're talking about these TCP IP on Ethernet networks. And this is exactly the place that Clockwork's tech can help a lot. As a final point, we're looking for beta users for validation. If anybody here is running workloads on Google Cloud that use these kinds of GPUs on TCP IP networks, we'd love to talk to you and explore how our technology can help you observe and control, improve the performance of your own workloads. So, thank you. Yeah, if there's any questions, I'm happy to take them. Yep.
So, is the support for the co-location, is it only for GCP or?
So we actually do run on various clouds. Oh, sorry. Yeah, the question that was asked was, is the scope for the co-location detector only GCP? No, we're actually able to run on AWS, GCP, or Azure for the co-location detector. Yes?
So I see most of your tests were distributed training. Have you run any tests for inference?
So far, our tests are, sorry, the question was, the tests were for distributed training. Have you done anything for inference? So actually, our tests were even one level below the training. What we were doing is actually just testing the NCCL communication primitives that are commonly used in training. And so, yeah, the most applicable thing here is for training. These primitives may or may not come up in inference, but that's something that we do need to study a little bit more. Yes? I'm sorry, can you repeat that one more time? Yeah, so the question that was asked was, is this applicable if we're using InfiniBand? So the observability part of it, we can do on InfiniBand as well, providing insights into network bottlenecks. But the controllability aspect right now is only supported on TCP/IP networks. Okay, cool. Thanks, everybody.